Welcome back to the wonderful world of astronomy. This is Chapter 5, Light and Matter, Reading Messages from the Cosmos. In this video, Part 7, Learning from Light, we're going to bring it all together, what you've been learning throughout Chapter 5. We started Chapter 5 learning about the structure of matter, and then we got into the properties of light and the electromagnetic spectrum. Now we're going to pull it all together and see what we can learn about the matter, the stuff that is out there in the universe, by interpreting its light. Here are two pictures. One is of a fire and the other of a blowtorch. And one of the things you'll be able to get from this is just to be able to discern things about the differences between these pictures, particularly the flame on the top, the orange flame, is cooler in temperature. Now they're both very hot, but the blue flame is much hotter. And when we look out in the heavens, we see stars of different colors. We see red stars, orange stars, white, blue, yellow stars, and that tells us something about their temperature. And there are many more things we can learn about what's out there based on their light, and so we're going to get into that in this video. Our goals for learning: what are the three basic types of spectra? How does light tell us what things are made of? How does light tell us the temperatures of planets and stars? And how does light tell us the speed of a distant object? There are three types of spectra, so you should know spectra is the plural of spectrum, and here you have them all three in a line right there, but let me break it down and look at them individually, the first one being a continuous spectrum. Here we have a light bulb, so an incandescent light bulb, which gives off white light. It spans all of the visible wavelengths. And so if we take this white light bulb and we shine it through a prism, this is just like sunlight, it's going to give off the full what's called a continuous spectrum. And there it is on the bottom, continuous spectrum, from red, orange, yellow to green, blue, indigo, and violet. Now notice the graph right here that's shown, wavelength, and so remember red is the longest wavelength of visible light, violet is the shortest wavelength, and then intensity. Intensity refers to how much power we get per wavelength, and it's not completely even, that would be a straight horizontal line, but it peaks about here in the middle, right at the yellow. That's a continuous spectrum. And we get such a spectrum from a star or from the sun. This is what Isaac Newton discovered when he took sunlight and put it through a prism and he got the continuous spectrum. But there are other types of spectra that are important in astronomy. An emission line spectrum. Now, remember from a previous video when we were looking at the energy in atoms, we were looking at the idea that an electron in an atom can be at an excited state, and when it falls down to a lower state, it loses some amount of energy and it gives off a photon of that same amount of energy. Now, that amount of energy is related to some wavelength, some color of light. So here we have, on the left, a thin or low-density cloud of gas emits light only at specific wavelengths that depend on its composition and temperature, producing a spectrum with bright emission lines. Now, we will get into later in this video what it has to do with their composition, but for now, I'm just giving you a general overview. So it gives off just specific frequencies of light. And this is an emission line spectrum, and it's called a line spectrum because you get these individual lines, not like the continuous spectrum that was just Roy G. Biv all the way across. Emission, because remember from previous video, properties of light, the four different ways that matter and energy interact, one of those was emission, so it's actually giving off the light. The third type of spectrum is not an emission line spectrum, but an absorption line spectrum. And remember, absorption is one of the other four ways that matter and light interact. So here we have a hot source of light. It could be a light bulb, but in astronomy, it's going to be a star or a galaxy. And we have a cold cloud of gas. A cloud of gas between us, we are the observers, so imagine we are here where the spectrum is being shown. So a cloud of gas between us and a light bulb or a star, something that emits light, can absorb light of specific wavelengths, leaving dark absorption lines in the spectrum. So the idea there is that, remember the hot source of light, the first kind that I showed you, it gives a continuous spectrum. So it gives off the full continuum of Roy G. Biv. And then as that light gets filtered through the cloud of gas will absorb the particular wavelengths that in the previous slide I showed you, it also emits those same wavelengths. So the absorption line spectrum looks something like this. It's the continuous spectrum that you saw in the first slide. However, there are these dips because it's absorbing. It's not letting those lights go through. So let's look at how does light tell us what things are made of. Here you see a sample of different elements, and each element gives off different spectral lines. So we'll talk about why that is. Remember back to the previous video, energy in atoms, and we saw how when electrons fall from a higher energy state to a lower state, they give off a photon that has the energy associated with the difference between those energy states. This is the same ladder rung diagram with level 1, otherwise known as the ground state, level 2, level 3, level 4, level 5, and many other levels, but they get closer and closer to each other as they go up. And when we are looking at that chart, if you remember level 1 over on the right, it said 0 electron volts, and then level 2, there was so many electron volts, 10.2 electron volts, and then 12.1. And I said those energy levels are specific to hydrogen. And it comes about, those quantities do, from the charges of the electron, how many charges are in the nucleus, given how many protons there are. And so every element, which has different numbers of protons, is going to have different energy levels, which means when the electron falls from one state down to a lower state, depending on the element, it will give off different colors of light. It will give off different energy photons. So the chart you're looking at here is specifically for hydrogen. So let's say that the photon falls from level 3 down to level 2. It will give off some amount of energy. Now, back when we were watching the video, when you're watching the video Energy in Atoms, we did subtraction of the energy levels, whatever the energy at level 3 was minus level 2, and that's how much energy it gave off in electron volts. Well, now we're going to see that that's related to a certain wavelength of light, 656.3 nanometers, which, by the way, is the color red. But if it falls from level 4 down to level 2, it's going to give off, that's a higher amount of energy, which means a higher frequency, which means a shorter wavelength, 486.1. If it falls from level 4 to level 3, that's a very small gap right there, a very small jump. And so it's not going to, the photon isn't going to have that much energy. So it's going to be low energy, which means low frequency, which means long wavelength. So 1875 nanometers, which is out of the visible range, it's actually in the infrared range. And so you can see, let's go over here to the right, falling from level 3 to level 1, that's a large gap, a large fall, so it's going to lose a lot of energy. And that corresponds to a wavelength of 102.6 nanometers, which is in the ultraviolet. Now, each type of atom has a unique set of energy levels. Each transition corresponds to a unique photon energy, frequency, and wavelength. So what this means is that we think of these spectral lines as the fingerprints. And there you see the title of the slide, Chemical Fingerprints. Every element has its own unique spectral lines because every element has its own energy levels. And so when the electrons fall from one state to the other, each element will give off its own specific group of frequencies. Now this is hydrogen right here. The downward transitions produce a unique pattern of emission lines. This spectrum shows emission lines produced by downward transitions between higher levels and level 2 in hydrogen. And these are the ones for hydrogen that we can actually see. So here we have 656.3, which is red, 486.1 nanometers, blue, 434, and 410 nanometers. Now, again, to the left off the chart is ultraviolet, and off the chart to the right is infrared. And the important thing to understand here is that helium, neon, carbon, all these different elements will give off their own different wavelengths. Now, when I described this, I described one electron. I said one electron falls maybe from level 3 down to level 1, or one electron falls from level 5 down to level 3. Practically speaking, we're not looking at one electron. If we have a mass of, as in this case, hydrogen gas, there are trillions upon trillions of atoms. And if they are excited, it means that trillions upon trillions of electrons are all going up to higher energy levels and then falling down. And it's evenly divided, relatively evenly divided. Some of them, of those trillions upon trillions of electrons at any given moment in time. Some are falling from level 3 down to level 2. Some are falling from level 4 down to level 1. And so we're getting all of these different spectral lines all at once. Because those atoms can absorb photons with those same energies, upward transitions produce a pattern of absorption lines at the same wavelengths. So I've been talking for the past few minutes about when electrons go down from a high state to a low state. But remember, in order to get up to that high state, they had to jump up. And if you remember back to the energy in atoms video, how did they go up to begin with? Well, they absorbed a photon. So a photon that has a particular wavelength, 486.1 nanometers, for example, if it comes in and it hits the hydrogen atom, the electron will absorb that photon of light. So hydrogen absorbs these wavelengths. And remember what we're talking about, the ladder rung diagram, where if it's not the exact amount of energy, it will not react, it will not go up. So let's say we get photons of 490 nanometers, which would be right about here. Well, that's an energy level that hydrogen will not react to, so it will not absorb 490 nanometers and kick the electron up to a higher level. So the same lines for a given element, in this case we're looking at hydrogen, the same lines that exist for emission lines are also absorption lines. And so we'll go back to this chart that I showed you earlier. Each type of atom has a unique spectral fingerprint. And here we can see just 5 of them: hydrogen, helium, neon, sodium, and mercury. Now, aside from astronomy, let's think about in everyday life, neon lights. And right there in the middle, those are the emission lines. Those are the colors that neon gives off. So with a neon light, it's a tube of gas filled with neon gas, and they run an electric current through it. When you switch on the light, you switch on the electricity, runs an electric current, and the electrons absorb a certain amounts of energy. And the electrons, while they are absorbing amounts of energy, of these trillions and trillions of these electrons, at any given moment, many of them are falling down to lower states. So they absorb and they immediately fall down. Meanwhile, other electrons are absorbing and then a split second later falling down. So at any given moment in time, you take a snapshot, you're getting all these spectral lines from neon. Now, your eyes do not see, when you look at a neon light, the blue and the green and the yellow and the orange and the red, but rather these lines, these different colors, they all combine together, and between your eyes and your optic nerve and your brain, they make one sensation based on those different frequencies. And it comes out, it looks just one color. It looks red to us. So a true neon light, which means a light that has neon in it, is always the color of red. Now, if you look at restaurants and businesses that have these things that we call neon lights, they come in a variety of colors, green, blue, purple, but if it's not red, it doesn't have neon in it, it has something else. So if you look at this, for example, sodium is sort of a greenish and a yellow, and sodium lights look kind of yellowish white. Mercury gives off other colors. Helium looks kind of like a lavender bluish. But so to get these different colors in these things that we call neon lights, they use different elements. Now in astronomy, the importance of this is when we look out at a star, for example, and we look at we use a spectrometer and we look at the spectrum and we see these particular emission lines. And the people who do this for a living, they recognize these particular lines as hydrogen lines. So they know that there is hydrogen there. And if they see these lines right here, they know that they're looking at helium. In fact, when they first saw these lines, it was in the mid-1800s, I think it was the 1860s, nobody knew about helium. Helium was actually discovered using spectroscopy, which is what we're looking at here, in the sun. They saw these unfamiliar spectral lines from the sun in the 1860s, and they didn't recognize them, and they realized they had discovered a new element. And it was actually named after the Greek word for the sun, which is helios, so it's called helium. And then about a decade later, helium was discovered in the earth, in mines under the earth. But helium was originally discovered in the 1860s using spectroscopy, finding these spectral lines in the sun. And so if they were to see these particular spectral lines right here in sodium, they would recognize those are the fingerprints of sodium. Those are the emission lines that only sodium gives off. And they would know that there is sodium in that star. When astronomers look at a star or a nebula or whatever out there, there's likely to be a large variety of spectral lines. And so it's up to them to recognize, to have studied these spectral lines and recognize them. What you're looking at here is actually in the ultraviolet. And these are spectral lines that are seen when looking at a nebula in the constellation Orion. So they're ultraviolet, which means they can't actually be seen by our human eyes. And so what happens is a spectroscope that is linked to a computer gathers the information and it records what wavelengths there are. And then it can produce a picture like this, color it blue so that our eyes can see it. But often when astronomers are doing spectroscopy, they're not actually maybe looking at a picture like this, but just looking at the numbers, the actual wavelengths, and they are trained to identify these wavelengths. Now, this one in particular, this Orion Nebula, shows a variety of lines. So here we have hydrogen lines, again, in the ultraviolet, and some helium lines. They are labeled up here. But look at this. These two lines right here in the middle, not just that they are oxygen lines, but they are oxygen with a +1 charge, so singly ionized oxygen. And look over here on the right, not just that this is a neon line, but it's the specific line that exists in doubly ionized neon. And there's slight differences, very slight differences in wavelength between neon and doubly ionized or singly ionized neon. Now, the presence of ions tells the astronomers that generally that there's a higher temperature, a pretty high temperature involved there, that there's enough energy in that environment to strip away electrons. Now, there are other nuances to it. They can also detect molecules. So, for example, we talked about one molecule, H2O, which is two hydrogens and an oxygen. And it's not just that they see hydrogen lines and oxygen lines, but H2O, the molecule, has its, or any molecule, has its own particular spectral lines because they have other modes of energy, giving off energy and absorbing energy, than simply just electrons being raised up and falling down. Molecules have rotation, they have vibration. And this picture you see here shows two spheres. Those are supposed to represent atoms, and it represents them as if there's a coiled metal, a spring between them. And so you can think about the vibration. If you took two of these spheres and had a coil between them, and you pulled them apart, they would vibrate back and forth. And so that is a metaphor for the electrical bond between the atoms. But the point here is that molecules have additional energy levels because they do these other things that single atoms don't do. They vibrate and they rotate. So we can use spectroscopy to learn to see that there are molecules in a cloud or on the surface of a star. The large numbers of vibrational and rotational energy levels can make the spectra of molecules very complicated. Many of these molecular transitions are in the infrared part of the spectrum. Now, let's look at another topic. How does light tell us the temperature of planets and stars? You look at this picture of a fire, and there's a metal poker in the fire. And when it's away from the fire, it's just the color of metal. Maybe it's a black color. And you get it closer, and it might glow red. And you get it even hotter, it could glow orange. It's possible it could glow white if it gets even hotter. And so we can tell the temperature of it, or get a sense of its temperature at least, by the color that the poker changes. And stars are very similar to that. Their color tells us about their temperature. And this gets into the topic of thermal radiation. We talked about thermal energy early in chapter 4 when we're looking at energy levels. Thermal energy has to do with the atoms that are moving around, the average kinetic energy, or the kinetic energy of the particles. Well, now we're going to look at thermal radiation, the idea that this energy radiates away into space. Nearly all large or dense objects emit thermal radiation. That includes stars, planets, and even you, the things in the room around you. They emit thermal radiation. An object's thermal radiation spectrum depends on only one property, its temperature. Let's look at a graph. We call it a thermal radiation curve or a thermal emission curve for various objects. Let's look first at the different axes, what it's telling us. So the horizontal axis is wavelength in nanometers. And notice on the axis we have 10 to the first, that's 10 nanometers, 100 nanometers, that's going to be in the ultraviolet. And there's the visible light, so we have 1,000 nanometers. Now we're getting into longer wavelengths that are in the infrared, 10,000, which is 10 to the fourth, and 100,000, which is 10 to the fifth. On the vertical axis, relative intensity per square meter of surface. What this means is it's showing for the different wavelengths how much energy, how much power is given off for each wavelength. We're going to look at a variety of objects. Let's look at the yellow curve right here. So this represents our sun, whose surface temperature is 5,800 Kelvin. And what it's showing is that at 10 to the first, so 10 nanometers, which is low wavelength, which is high frequency, the sun doesn't give off any of that. But we come to 10 to the second, it gives off a little bit of ultraviolet, around 100 nanometers. And as we get longer wavelengths, it gives off more and more. And we go to the top, and it actually peaks. The wavelength that gives off the most of is about 500 nanometers, which is right between green and yellow. And then it goes lower and lower and lower into the infrared, and eventually we get to long enough wavelengths and the sun doesn't give off those longer wavelengths. But if you zoom in, you can just at the visible light, so it gives off a lot of violet, a bit more blue, a bit more green, some yellow, a bit less orange, and a bit less red. And all of those frequencies in those relative intensities combine in our eyes to see a yellowish whitish star. Now let's look at the blue curve. This is a higher temperature star, 15,000 Kelvin. Notice that all aspects of the curve are higher up than the yellow, so it is more intense. It is a brighter star. than the sun. And notice it is giving off the ultraviolet on the left and it's giving off the infrared on the right. But let's focus on the visible right here. It's giving off a lot of violet and less blue and less green and less yellow, less orange and less red. So it's giving off all those colors, just like our sun does, but in varying relative intensities. It gives off more on the lower wavelength or the higher frequencies. This will look like a blue star to our eyes. Now, it's giving off more violet than anything else, but our eyes are not that sensitive to violet, and it's just the combination of all of those colors in those intensities, and we will see it as a blue star. Let's look at the red curve. This is a much cooler star. This is as cool pretty much as stars get. Surface temperature of about 3,000 Kelvin. So it gives off a lot more in the infrared. Not too much ultraviolet. Notice that it peaks in the infrared. That's the highest wavelength, or the wavelength of the most intensity that it gives off. But to think about what color we're going to see it, we take the combinations of a lot of red, not as much orange, not as much yellow, and decreasing intensities of green, blue, indigo, violet. Our eyes and our brain combine all those in those intensities, and we will see it as a red star. Also, by the way, notice going back to the hot star, the blue star, it peaks in the ultraviolet. Okay, one more thing. A human body, very cool compared to stars. 98 degrees Fahrenheit, 37 degrees Celsius, or 310 Kelvin. Now, it is a much shorter curve. So being cooler temperature, we are not nearly as bright as stars are. And the wavelength is around 10 to the fourth in infrared. So whereas we do not emit visible light, we do emit infrared light. And this is the basis of a lot of night vision technology. There are different kinds of night vision technology, but the fact that our bodies emit infrared light. So with an infrared camera, you can see people. And now let's think about the electromagnetic spectrum. The idea is that the hotter the temperature of the object, its main wavelength, we call it the peak wavelength, is going to be a higher frequency. And so, for example, let's look down at the bottom of the chart. The sun, the surface of the sun at 5,800 Kelvin, it primarily gives off visible light. But there's a hotter region of the sun known as the chromosphere, and we'll study the parts of the sun when we get to chapter 14. The chromosphere is a higher temperature, about 10,000 Kelvin, and it actually gives off more in the ultraviolet. And then you have very hot things in space, such as the accretion disk around a black hole. Those get up to millions of Kelvin, and being much, much hotter than the surface of the sun, they actually give off X-rays, higher frequency. Let's go to the other end of the spectrum, planets and clouds that form stars, meaning they're not yet hot enough to be stars, but they are forming into stars. They are much cooler temperature than the sun, and so they, like people, human bodies, they give off infrared. And then there's the very cold of space, what's known as the cosmic microwave background. Very cold. It's only about 2.7 Kelvin, just a little above absolute zero, and it gives off microwave. So here's our thought question. Which of the three is the hottest? A blue star, a red star, or a planet that emits only infrared light? And when you evaluate this question, I want you to think in terms of frequencies. The one with the highest frequency is going to be the hottest one. And so infrared of these three is the lowest frequency. It's below red. And then between blue and red, remember blue is the highest frequency, which means the highest energy. So it is the hottest temperature of those. And you look at the pictures down below. There is a blowtorch, a blue flame from a blowtorch is very, very hot. What we consider a normal fire might be yellowish orange, and so kind of medium among these pictures. And then we have a stove burner, which is reddish orange. And so that reddishness tells us it's a cooler temperature than the others here. So based on what you've learned so far, talking about thermal radiation in this video, why don't we, meaning humans, why don't we glow in the dark? And the possible answer is people do not emit any kind of light. People only emit light that is invisible to our eyes. People are too small to emit enough light for us to see, and people do not contain enough radioactive material. It's useful with multiple choice questions to be able to eliminate the ones that are definitely not the true answers. And so if you look at question D, well, we haven't even in this class talked about radioactive material, and so you can probably eliminate D. People are too small to emit enough light for us to see. Well, light bulbs are much smaller than people, and yet they emit light, so it can't be C. It's got to be either answers A or B. What do you think? So earlier when I showed the thermal emission curve, I showed that answer A can't be correct. People do not emit any kind of light because in fact we do emit infrared light. But answer B is correct. People only emit light that is invisible to our eyes. So what colors are stars? Stars are generally thought to be these 5 different colors. Now there's a bit of a continuum between them, but in general we talk about 5 colors of stars: red, orange, yellow, white, and blue, going from coolest to hottest. Now that looks almost like the spectrum of the rainbow, and so I call it modified Roy G. Biv. It starts out like the rainbow, Roy, red, and we get higher frequency, which means higher temperature, orange, and then like our sun, yellow, Roy, but then there's no green, and there's no violet on the very end, and then there's white. So what's going on here is if there is the right relative intensities between the colors, such as I showed you that for our sun, which is generally regarded as a yellowish whitish star, it's a pretty even spread of those frequencies. Whereas when I showed you a red star, it was very high in the red and lower in the orange. And all these colors have to do with is how our eyes and our brain perceive the different wavelengths. And so if it's hotter than a yellow star, it's a nice perfect spread of the frequencies that it will just look white to our eyes. It's a spread of all those different colors. And then blue. And as I showed you in the thermal radiation curve on a previous slide, it's already peaking in the ultraviolet if it's blue. And so peaking more to the ultraviolet isn't going to make it any more purple, just because our eyes are not that sensitive to purple or violet. So the hottest star, we will perceive it to be a blue star. Now, these are all matters of perception. And sometimes 2 people looking at the same star, one might say that's a red star, the other might see it as an orange star. So some of it is perception. But again, in general, we regard stars as having these 5 different colors: red, orange, yellow, white, and blue. Important to note, there are no green stars and there are no purple stars. That is the end of the part 7 video, Learning from Light. Have a great day.